All right, folks, it's Bass Action back in action here. In this video, we are going to go through the first of two examples for how to graph a complete rational function. The first thing that I want to call your attention to is the fact that I've got 7, well, really 8, if you count the last ones there. I've got all these steps typed out here, and I want you to know that each individual step could represent an individual question I might ask. But also, if I ask you to graph a rational function just on its own, you are expected to know all of those steps and know which ones you need to do. Now, sometimes some steps can be skipped and some steps will actually answer the question for another step, but you should be aware of all the questions that should be asked each time. Now, the very first step actually is the one step that can never be skipped and must always remain at number 1. Other steps can potentially be rearranged, but never this number 1. This number 1 step has to stay here. And that step is to factor and find the domain. Now, you can see that I have started factoring this function already. I didn't quite finish it. We could finish off this x minus 3 and an x plus 3 here, and then we could find our domain. Now, domain is something that we've been doing for a long time. And we know that with a rational function, the only thing we're concerned about is where that denominator might become 0. So those are pretty easy to identify now. We're going to write this in our set notation, x such that x is not equal to a negative 4. And if you would like to write the plus or minus 3, I'm totally okay with that. The next thing that we're going to do is we're going to reduce the rational function in any way that it might reduce. Not all of our rational functions will reduce, but sometimes they will. So if they reduce, as in this one where the x plus 4's cancel, we're going to go ahead and cancel those and rewrite our function without those terms in it. So we're going to just look at this x plus 2 over x squared minus 9. Now, from here to the very end of the problem, this is the only function that we are concerned about. We are never going to look back at that original function again. You can pretend it doesn't even exist. We only needed it to find this domain. The next thing that we're going to do is we're going to find the holes. Now, a hole is going to happen if something in that step 2 actually canceled. So on this problem, we did have something that canceled, that x plus 4 canceled, so we're going to use that value to find a hole. So since the x plus 4 canceled, that means that at x equals a negative 4, we're going to have a hole. Now that's only half of an ordered pair, so we need to finish that off. So we're going to evaluate, of course, our reduced function at a negative 4. So when we plug that in, we're going to get a negative 2 in the numerator, a 16 minus 9 in the denominator, so we're going to get a negative 2 over a 7, so our hole is going to happen at a negative 4, negative 2 sevenths. We'll just save that for a little bit. When we get to our final graph, I'll show you how to use it. The next thing that we're going to do is, again, using the reduced function, we're going to find our vertical asymptotes. The vertical asymptotes are where the denominator equals 0. So we've actually already identified those when we did the domain. Notice that this negative 4 is no longer a vertical asymptote. The negative 4 became a hole. We still have this plus or minus 3. Now we're going to go ahead, we're going to write those separately. It's not that it's required, but it is a nice visual reminder when you go to actually do your graph. So as I just mentioned, the values that you identify in the domain are going to either become a hole or a vertical asymptote. They must become one or the other, but they cannot be both. Step 5 says to find the horizontal or the oblique asymptotes. Now, we're going to come back here. We're going to look at this reduced function. We're going to look at the degree in the bottom and the degree in the top, and we can see that our degree on the bottom is bigger. So this is what we've been calling a bob. So this is a bob, it's bigger on the bottom, and on a bob we follow our rules, and that tells us that the horizontal asymptote is automatically y equals 0. The next thing that we're going to look at is whether or not our graph is going to cross this horizontal or oblique asymptote. Now this is a new concept for you because you've been accustomed to things never crossing asymptotes. Horizontal and oblique asymptotes are unique though in that they can cross them. So what we're going to do is we are going to look at the fact that our horizontal and our obliques will be written as a y equals. And then when we look at our function that's in this function notation, that's just a fancy way of saying y. So now I know that y is this and y is 0, so I can set these two equal to each other and solve. If you get a valid answer, then it will cross. We'll see what that looks like here. So we're going to have an x plus 2 over an x squared minus 9. That's going to equal the 0 from the horizontal asymptote. I can go ahead and I can put this right side over 1, cross multiply, and I'll get an x plus 2 equals a 0. So at x equals a negative 2, it's going to cross. So we can write that nice ordered pair, negative 2, comma 0, because again, that's just coming from that asymptote. The next thing we're going to do is we're going to find our intercepts. Now, if you're paying attention, you can see that this crossing happens to be one of our intercepts. A graph can cross a horizontal asymptote and it's not an intercept. It's just a coincidence here. So this one is our intercept, but when we go find our intercepts here, we're going to pretend that that didn't happen so that you can just see a reminder of what you would do. So if you needed to find your intercepts, you would let, for example, y equals 0 in your reduced function. So we would take our reduced function, we would set that then equal to 0, we would solve it. Now you can see that's the same thing we just did. So sure enough, our intercept is negative 2, 0. Then for the y-intercept, we're going to let x equal 0. And for our y-intercept, we're going to get a 2. I'm just coming back here and I'm letting this x is 0. So the x drops out, the x squared drops out. So I'm going to get a 2 over a negative 9. So the y-intercept is going to be 0, comma, 2/9. Okay, so now we've got our intercepts. Now we're going to go down here to the bottom and we're going to start putting the whole thing together. Now I'm going to scroll this up past where we were, but you've still got yours in front of you so you can see where I'm getting all my information from. So the first thing I'm going to do is I'm going to draw in the vertical asymptotes, and I really want to emphasize that these are sketches. So they don't need to be to scale, but they should generally make sense. So notice I'm making these really far away from these vertical asymptotes from the center there. Actually, this one looks pretty far off. It doesn't look very symmetrical. I'm going to erase that. I'm going to make that a little better for you. So let's make that one just look a little bit more symmetrical for us. That looks a little nicer. Okay, so we've got our vertical asymptotes. We've got our horizontal asymptote. Then we have our intercepts. Okay, so we've got our two intercepts here. And our intercepts are going to be at a negative 2 and at a negative 2/9. Now, that negative 2/9 is really hard to graph because it's so tiny. So I'm just going to scooch it way down because who cares? It's just a sketch. It just has to give us a general idea of the shape. Then what we're going to do is we're going to start looking at the behavior around these asymptotes. Now, if we're remembering from up above the fact that we had a hole, okay, we had a hole at a negative 4 and a negative 2/7. So we're supposed to have a hole in the graph somewhere around here. Oops, wrong one there, sorry. Then we should have a hole somewhere around here. Now, what that's telling me is that my branch of my rational function needs to be here to create this hole. It's probably not up here. It's going to be somewhere down here. Now, the way we verify that is called analyzing the behavior near these vertical asymptotes. And you can see I've written out this new kind of a notation for you here, all right? And when I use this new notation, what this notation is telling me is that this value right here identifies what vertical asymptote I'm looking at, and this negative up here tells me whether I'm looking at that on the left or the right side. So in this case, it's going to be the left because it's a negative. So I'm looking at something on this side. So what I'm going to do is I'm going to pick a value for x. In this case, I'm going to pick a value of negative 3.5. X equals negative 3.5. And for our purposes, and just to make this a little clearer, I'm going to rewrite our function here. We had an x plus 2, and we had an x squared minus 9. So what I want to know is that if x is a negative 3.5, what happens to this? Do I get a positive or a negative number? I do not care about the number itself. I just want to know, do I get something positive that tells me my graph should be up here around the asymptote, or do I get something negative that tells me it should be down here around the asymptote? And when I put that negative 3.5 in, I can see that I get a negative number in the numerator, and in the denominator, a negative 3.5 squared is going to be bigger than 9, so I'm going to get a positive number in the denominator. Well, negative over positive is negative, so this graph must be going towards negative infinity, and that makes sense for where we thought our hole should be. Now, on this middle part, I already have some clues. My intercepts are actually telling me a lot about what my graph should be looking like, because I have to cross through these. So I can guess that my graph is supposed to go up here. It's supposed to somehow cross through those. I don't know exactly, and it doesn't really matter for our purposes. It's going to somehow squiggle its way through there. Now, if you wanted to go and actually test this, you could pause the video and you could let x equal, let's say, a negative 2.5. Now, this is an important value that I'm choosing here on this graph because I have an intercept right here and I have an asymptote. And when I'm trying to test this behavior on this right-hand side of this asymptote, I have to always pick a value between the intercept and the asymptote, okay? It has to be between there. If you don't, it's not going to work. Now, if you go ahead and you test that, what you should find is you'll get a negative value in the numerator for your function. You'll get a negative value in the denominator for your function. So negative over negative is positive. That is why our answer will in fact be a positive infinity. You could test this one as well. You could pause the video and test this. The value I chose when I tested it, since I didn't have an intercept to worry about, was I picked a 2. I'm just picking a number that's on the left-hand side of the asymptote. Remember, this negative right there is telling me I'm on the left of that vertical asymptote. And when I did that one, I had a positive over a negative, and that gave me a negative infinity. Then I'm going to come over here and I need to test on this right-hand side. Now this one we have to test. We had a clue on this part, we had some clues on this part, and on this part we don't have any kind of a clue. We don't know if our branch is supposed to look like this or like this. So we're going to have to test on this one. So remember, the 3 tells us what vertical asymptote we're looking at. The plus tells us that we're on the right-hand side of that asymptote. And then we're going to pick a value. So our value that I'm going to choose here is I'm going to let x equal 4. I cannot emphasize enough, we don't care about the number, we only care about the sign. So if an x is 4, when I put it in my numerator, I'm going to get a positive. When I put it in the denominator, I'm going to have a 16 minus 9. I'm going to have another positive, so I'm going to get a positive infinity. So my, on the right-hand side, needs to be up here, pointing up, which means the rest of my branch needs to come down and approach the asymptote. Now I'm going to throw one last thing in here. It's a concept students have struggled with in the past, and I'm going to write the limit notation for you. So I want to understand the limit of my function, so what's happening to the function when my x value goes towards negative infinity. So what happens to my graph as the x values get smaller and smaller, or I should say bigger and bigger in the negative direction is an easier way to think about it. Okay, so what happens when they go out here? Well, when I look at my graph, I can see as I trace the graph, they are getting closer and closer to my horizontal asymptote of 0. So the limit as it goes to negative infinity is 0. On this right-hand side, I'm going to write that limit notation again. What is the limit of my function as my x values go to positive infinity? So as my numbers get bigger and bigger and bigger and bigger, what's happening to my graph? And I can see, just looking at it, that the graph is getting closer and closer to 0. Okay, so we've put everything up here on the graph. We've got everything pulled together. You might need to pause. You might need to jot down some questions. And when I give you your practice, you're going to have a whole bunch more to do. And there's a video, one more video of one more example.